In the last video, we obtained this solution for the free particle wave function, giving us this function psi that depends on k, where k corresponds to the energy, and k being greater than 0 represents a wave traveling to the right, and k less than 0 represents our free particle wave traveling to the left. And given that k represents the energy, these wave functions should correspond to the definite energy states of our free particle, which means we should be able to normalize them. So you can imagine if we have some free particle with some specific energy, then we want a measurement of that particle to give us back that wave function, that eigenstate, with probability 1. And what that says mathematically is that the inner product of psi of k with itself, which is equal to the integral over all of space of the probability density squared, should give us back 1, which means we should be able to normalize it by a correct choice of this complex amplitude A. So let's see what happens when we try to do that. We can pull out this magnitude squared of the of A here, what is our normalization constant. And then, but the modulus squared of any exponential is just 1. So we have this integral, just d of x over all of space, and of course this gives us infinity. So there's no correct choice of A for us here, and that means we need a new way of looking at this. And it says something kind of subtle about the free particle, which is a little disturbing, and that is there's no such thing as a free particle with definite energy. So that's a pretty interesting conclusion. And how are we going to proceed from here? How do we make sense of the solution that we obtained for our Schrodinger equation, which hasn't failed us up until now? And it turns out there's a different way of looking at this. Instead of having a linear combination of these discrete states of the free particle, what happens is we get something called a wave packet, where we're not taking a sum anymore, but rather an integral over a range of different energies, different k values. So what that looks like is we're going to get this full solution, and I'm not going to put k here anymore because this is not one specific k, but it's the entire range of them. That depends on x and t, and like I said, it's not a sum, it's an integral. But now that we're integrating over a range, we need to include some sort of function that depends on k, and these are like the varying amplitudes for the different states, the different k states, but now we have a continuum of those states, and then we just have our exponential here. And now I'm going to write omega in terms of k again, which is h k squared over 2m t. And remember, we're integrating with respect to k because we want to integrate over this entire range of k values. And it turns out we can normalize this wave function. It's kind of interesting that going from a sum to an integral actually allows us to tame our infinities and bring it down to a finite value. So, of course, the next step here is how do we actually determine what phi of k is? So the way that we do that is we take t equals 0, so the starting time, and then we just look at this wave function, because now we no longer have a time dependence, and we can recognize that this is a familiar scenario in something called Fourier analysis. And Fourier analysis is essentially a branch of math that studies how one can decompose functions into these component parts, which are periodic functions of that variable. And it's very interesting, and there's theorems that we can use now to actually make sense of this and figure out what 5k must be. And the theorem that we're going to refer to, which I'll present now with no justification or proof, it's called Plancherel's theorem. And this relates the Fourier transform of a function to its inverse Fourier transform. And it looks like this. So you have some function f of x. And here we pull out this factor 1 over the square root of 2 pi, which is just convention and makes things nicer. And I mean, we could have done the same thing up here and here. And what this theorem says is that this integral with this function that depends on k, which we're integrating with respect to over here, is equivalent to the following. This other equivalence that we have here. Where the sign of this exponential is flipped, and now we're integrating with respect to x. So this is a kind of interesting relationship between two different variables and these two exponential functions and these integrals that integrate with respect to the other variable. And you can start to see how we can quickly use that to figure out what phi of k is in terms of our psi of x at the initial starting time, which is t equals 0. And recall that this is usually the way it goes in quantum mechanics. You're usually given this, and then you want to use that to determine this. So if we're given this, and this is the only remaining unknown, we can use Plancherel's theorem to solve this quantum problem, which is what is the wave function for the free particle. So in the next videos, we're actually going to do that, but there's going to be a preliminary video where we actually somewhat justify Plancherel's theorem, because I understand presenting like non-trivial theorems like this is not very satisfying if you don't have some sense of where it came from. So we'll do a sort of sketch of a derivation of it based on some weaker assumptions. And yeah, that'll be in the following videos. So thank you.